G'day grade 12s, we are looking at the September 2019 EC mock exam for grade 12, paper 2. This is a chemistry paper. We're going to start by looking at question 6 here. And what we're going to do is we're going to have a look at this section, which is focusing around chemical equilibrium. Okay, this is your KC calculation question. That's what it's known by, and it's what I've come to know it by. So let's have a look at question 6. Of course, we start each section on a new page. The decomposition reaction of hydrogen iodide, Hi, represented by the balanced equation below, reaches equilibrium in a closed container at 25 degrees Celsius. And we have the decomposition reaction there. 2Hi in the gas phase goes to H2 gas plus I2 gas, and we have enthalpy there. Delta H is greater than 0. 6.1.1 asking, how does the rate of this forward reaction compare to the rate of the reverse reaction for the at the following stages? Choose from higher than, lower than, or equal to. Well, the first one for 6.1.1, they're asking, at equilibrium, how does the rate of the forward reaction compare to the rate of the reverse reaction? Well, at equilibrium, that's pretty basic, that's pretty simple. Okay, we'll write down. Let me just get my board open. Okay, this is question 6. Okay, so for 6.1.1, we'd write down equal to, because if the reaction is in equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. 6.1.2, before the reaction reaches equilibrium for the first time, reminding us about the question again, how does the rate of the forward reaction compare to the rate of the reverse reaction at the following stages? Remember, we are decomposing, so this is our forward reaction, and we want to know before the reaction reaches equilibrium. So just before it reaches equilibrium, it will be higher than. Alright, and we can determine that by just drawing a rough sketch of the potential energy or reaction rate graph. Alright, because we know, because of this value here, that it's an endothermic reaction. 6.2, what effect will an increase in pressure by decreasing the volume at constant temperature have on the concentration of hydrogen H2 at equilibrium? We need to choose from increase, decreases, or remains the same. Let's just have a look at that question again. What effect will an increase in pressure by decreasing the volume? So by decreasing the volume, we increase pressure, and by increased pressure, we decrease the volume. So essentially, what we're doing, we are decreasing volume. Okay, but temperature is constant here, so we decrease the volume, which in effect increases the pressure, while temperature is constant. What would that have on the concentration of H2? Well, by doing that, according to intuition and according to study, that would definitely increase the concentration of H2 at equilibrium. 6.3 is our KC calculation, our actual KC calculation. They say the reaction is started by pumping a certain amount of hydrogen iodide into an empty flask, which is then sealed. The equilibrium concentration of two of the substances at 25 degrees was found to be 0,026 mole per decimeter cubed for iodine and 0,72 mole per decimeter cubed for hydrogen iodide. Now they say when the temperature of the equilibrium mixture is increased, the equilibrium position shifts and a new equilibrium is established at 448 degrees Celsius. At the new equilibrium, the concentration of hydrogen H2 is found to be 0,084 mole per decimeter cube. Calculate the equilibrium constant for the reaction at 448 degrees Celsius. Now this question is slightly different from your normal KC calculations, okay? But we still set it up the same way. In terms of we still set it up with the same table or similar table. The difference here is that we're not calculating initial moles here, and the change in the mole to get the equilibrium mole to get the equilibrium concentration. We have been given equilibrium concentration or initial equilibrium concentrations, and then now we have a shift in equilibrium where we find a new concentration. So in this question we are working with just concentration. So how that table would look, I will set it up on a new page, is we still have our reaction to, wait, that's a little far, 2HI, hydrogen iodide, okay, I just write down the entire reaction here, and we get H2 plus I2, okay, we don't have to include the phases for this part, okay, and understand we have the ratio of 2:1:1, so I write down my ratio like this, and then I include that in my table. Okay, and I leave this section here for my values I'm going to put in. Okay, so what we do, I know that I was given initial concentration at a certain level. I do know there must have been a change in that level of concentration. And I also know there must be a new equilibrium concentration. So I'm just going to abbreviate it to CEQ. EQ for equilibrium. Okay? And this is for, let me just split it up into the desired different sections for the different elements. So initially they did tell me that at the first equilibrium, concentration of two of the substance at the original 25 degrees Celsius was 0,026 for iodine, I2, 0,026, and it was 0,272, for hydrogen iodide. Okay, now of course we know what to do. We can see that for these two, hydrogen and iodine, they're in the same mole ratio, so we enter the same value, the same concentration value for H2 because they're in the same mole ratio. Okay, then they told us further down the question that a new equilibrium was discovered because it shifted to 448 degrees Celsius, and they said at the new equilibrium the concentration of hydrogen was found to be 0,084. So we enter in here the 0,084 because this is the equilibrium concentration. So now that we got the equilibrium concentration, what do we do? Okay, first of all, we know that we need to find a value for the change in the concentration that must have happened for us to get this value. Alright, so I'm just going to grab my calculator from my bag. Just one moment. So we take the equilibrium concentration minus the initial concentration would give us by how much this concentration had to have changed by. And when we do that, we get a value of 0,058. Okay, and when we get the 0,058, we know because these two are in the same mole ratio, they have the same values. So the same concentration of hydrogen at equilibrium must be the same concentration for iodine at equilibrium. So it's also 0,084. But of course we know these two values here for hydrogen iodide, Hi, is going to be different. Okay, we know that's in the mole ratio of 2:1:1. So we have to multiply these two values by 2 to get what the change in concentration and the equilibrium concentration value is at this new temperature of 448 degrees. So if we take our change, 0,058 multiplied by 2, or divided by 1 first and multiplied by 2, that should give you 0,116. And then if you do the same thing here with 0,084, and you multiply that by 2, you would get the, sorry, you don't do that for the equilibrium, sorry. We take our initial for this one, initial 0,72, and we minus it from or we minus rather 0,116, because we know this is a change. This is what was lost, of course, and we get a value of 0,604. Okay, like I said, very similar. Apologize for that. And now we've got a full table, so now we can go and calculate the equilibrium constant, of course. Okay, so what we're going to do is we're going to, okay, I'm going to see what I'm going to use a new slide. We start Kc, okay, it's a capital K. Kc is equal to the concentration of our products, in this case, which was H2, concentration of I2, concentration of hydrogen times the concentration of iodine, all divided by the concentration of hydrogen iodide to the power of 2. The reason why it is squared is because the balancing number 2 was in front of it. We know those equilibrium concentrations for hydrogen and iodine to be the same value, so we can just take 0,084 times 0,084, which is the same as 0,084 all squared, and then we're going to divide that by 0,604 all squared. Okay, brackets just neatens it a little bit, and once we do that, we'd get a value for the Kc calculation. Therefore, the equilibrium constant at the new temperature, 448 degrees Celsius, is 1,93 times 10 to the power of -2. It's an equilibrium constant. It doesn't get a unit of measurement. It's just a constant. And then the final question in 6.4 asked, what effect will the increase in temperature from 25 degrees to 448 degrees Celsius have on the rate of the reverse reaction? Choose from increase, decreases, or remains the same. So now we're increasing the temperature from 25 to 448, and we want to know what effect would that have on the reverse reaction now. So not the decomposition, which was the forward, but now the reverse being the composition of hydrogen iodide. You want to know what effect will the increase have on the rate of the reverse reaction. Remember, paying attention to the word rate. Alright, the time it'll take for the reaction to complete. We know that if there's increase in temperature, there's increase in kinetic energy, meaning that the rate of the reverse reaction now, at this new temperature, we choose increases. And 6.4 wraps up question 6 for this paper, as well as the chemical equilibrium section of this chemistry paper. Please stay tuned for more videos where we will look at a couple more sections of this paper.